Section 4.3 is all about ways to check if a linear regression is the correct regression to use. And we'll go through a bunch of different things. Some of these things won't be on the test, but I still think it's important that we go through these concepts, mostly just so you see them, and if you ever have to use them in a different class, you've at least seen them at once. Okay, so the first thing that we can look at is called the residual plot, and it's the scatter plot of the x coordinates and then with the residuals. And we can see if there's like a pattern among the residual plot, and that may indicate that it's not appropriate to use a linear regression. The ideal with the residual plot, actually with any type of regression, is that the residuals are scattered throughout the plane that's shown. So for this one, we're looking at distance in meters and the record time in seconds. And we want to make a scatter plot and look at the residual plot for this one. So I have the data file open, and I'm just going to copy and paste this into our linear regression file. And get rid of the extra ones at the bottom here. And it does all this calculation for us, and we can see that it's looks like a straight line, right? One thing, so the correlation is strong, very strong actually, but we look at the residual plot and it looks like it has this curved pattern. So going down and then back up here. When we see a pattern in the residual plot, it typically means that we've chosen the wrong type of regression to use in the situation, or with the variables that we're measuring. So for this one, even though it does look like a very strong correlation, it wouldn't be most appropriate to use a linear regression in this situation. I would think that because of that acceleration time at the beginning, we don't start out at full speed. Because of that acceleration time, it would probably be better to use like a square regression. But yeah, so let me just write down here a couple of sentences. So if the residual plot has a pattern and I'm just going to put like for example here. If it's something like this, like has dots, if it has a linear pattern or a quadratic pattern, something like that, then a linear model may not be appropriate. If the residual plot has points dispersed. Throughout. A linear model. May be appropriate. And so for this one, just note this here. For this example, it does have a pattern. So a linear model may not be the best. To choose. Okay. So yeah, you gotta kind of look out for that. It's always a good idea to look at a residual plot just to make sure it doesn't show anything that's kind of weird. Okay, now another thing, unusual points are points that fall away from other points on the scatter plot. There's two different categories of unusual points. One is called a influential observation, and this is far away in the x direction. And typically what you do with this is you remove it and see if it changes the model significantly, or then you keep it in there at first and then you remove it and you see what the difference is between the two. The other unusual point is called an outlier, and this one has a larger residual, so it's in the y direction. It's really different in the y direction. So let me just note, this is like in x direction, it's different. And then outlier is different in the y direction. Okay, well, most of the time, if it's having a huge effect, you want to at least talk about it. Sometimes you may choose to remove it from your set of data. Just make sure that you do note that if you would be running a study. So example 2 here says, consider the data on age versus the weight of black bears. You have a bunch of ages there, a bunch of weights. And I'm going to take this data and plug it into our file, the linear regression file. And it's asking which point is an influential point. And then it's also asking what happens to the slope and intercept when you remove this influential point. So let's do those questions at the same time we look at this data. So I'm going to copy and paste that data into this file. And we see this influential point. It's far away in the x direction of 28.5 and 62. So a fairly old black bear in comparison to the other ones. And what we can do is remove the plot. remove that point and see what happens. So let me just copy this down. So before removal, we have the least squares line that's written there, right here. I just copy this down. Maybe not all the decimal places, but just a few. And then after removal, so to remove the point, I'm just going to go over here. It's this 28.5 and 62. Just press delete on that. That gets rid of the point. You don't have to move this around. You can really just leave it like this. And we get a new line. They're all kind of close to each other, but the least squares line right here has changed. And it has changed fairly significantly. Just copy this down real quick. Yeah, so it has changed significantly. So let's go back here. So here's the comparison of these two. The slopes are pretty significantly different. Those are pretty significantly different. The y-intercepts aren't as different. These are fairly close, but the slopes are pretty different. This is almost double this, so it's changed pretty significantly. So yeah, a point like that, we would probably be like, okay, this is we're just gonna remove this data point. Let's just get rid of it and say that's influencing it a little bit too much. Now, before we move on, I want to talk a little bit about the interpretation of the slopes. And this is an important thing, even in 4.1, 4.2. The slope takes on units of y over x. Think of how the slope is calculated change in y over change in x. So this slope would be 1.144. The weight is in, it doesn't say. I think it's pounds. So it's in units of the weight, the y coordinate. So pounds divided by the x coordinate, in this case age. This is going to be in years. So pounds per year. Once you have the units, I think it really helps with the interpretation, because I see this, I say, okay, 1.144 pounds per year. So that means it's the weight is increasing at 1.144 pounds per year. And this is for black bears ranging from 5.5 to, once we remove that 28.5, to 11.5 years. So ranging between those two values. The y-intercept is a different interpretation. I just put weight increases 1.144 pounds per year. That's can be an interpretation of our slope. And then the interpretation of the y-intercept, this one's kind of strange because age of 0, or x being 0 would be age of 0. That's like right at birth. So this is kind of, well, this is a pretty horrible interpretation, right? And that would make sense. We're extrapolating. We can't. We don't have data right at birth, so this is an extrapolation, and it would say at x equal to 0. I'm just gonna put at birth. A black bear weighed, or a black bear weighs 41.809 pounds. That's crazy. So this is a bad a bad extrapolation. Let's just put that. So we would predict this, but any reasonable person would say, okay, that's a ridiculous extrapolation. That it just doesn't make sense. Baby bears wouldn't be that huge at birth. Okay, now another thing to talk about, the coefficient of determination, which is r squared. A lot of times people will just say r squared instead of coefficient of determination. It's the proportion of variability in the y variable that can be quote-unquote explained by this linear relationship between x and y. The larger the r squared value, the larger the proportion of the variability that's explained. If you do the complement of that, you can think of it as the unexplained variation. So there's variation that's changing it that we just can't explain. It's missing. Okay, so here, let's look at this example. House prices in houses in Bethlehem Township, and they're given the square footage, and it's asking how much is explained, quote unquote, explained by the square footage of the house. Okay, so to get this, copy and paste the data. And I'm just going to do that over here. Pretty quickly. Get those in there. It gives us our least squares line here. We can think of this $122.56 per square foot. So increase it by 1, increase the asking price by $122.56. The y-intercept, a house with 0 square footage, an empty lot, $172,818.45. So also an extrapolation, but something that you could do. The coefficient of determination is right here, 0.5334. 53.34% is explained by the square footage of the house. Let me just write that down. Okay, so about half the price, little over half the price is explained by the square footage. So we're missing missing all those other factors that go into a price of a house. Okay, now another thing here, I talked a little bit about this before. It's standard deviation about the least squares line. It's S subscripted with an E. We're not going to use it very much. Actually, I don't think we'll use it really at all in this class. It's typically used in making confidence intervals for predictions. It's calculated in that linear regression Excel file if you ever need to do the calculation. Okay, now things to consider when doing a linear regression. Does the data appear to be linear when plotted? It's always a good idea to check. Does the residual plot look appropriate? So does it have a pattern? If it does, might not be appropriate to use the linear regression. Are there any unusual points? This is all the stuff we did just before. Look at the value of the correlation coefficient, the R value. What's the R squared value? And then the standard deviation of about the least squares line. Make sure that's not huge. Also then, are you interpolating or are you extrapolating? Make sure you determine which one you're doing. So I just want to show you one thing which I forgot to put in the notes. So that Oncombe quartet, it's called. So this is something, let me pull this up. So it's important that you actually look at the scatter plot itself. So looking at this, these 4 data sets have exactly the same least squares line, exactly the same R value, but they look very different, right? This one, it looks like it would be appropriate to use a linear regression. This one looks like it's like a parabola, right? So not appropriate to use linear regression in this situation. This one, all of these are falling into one line, and then we have this one point up here that doesn't fall on that line. So it's like, it's unusual, right? It's I guess not unusual. Yeah, unusual. The outlier was the one. It's different in the y direction. So no, using this line doesn't seem appropriate. And then this one here, this influential point, all of these are at 8, and then this one is at, looks like 18 or 19. It has the same linear regression line, same correlation coefficient, but it's only appropriate in this one situation. There's another one called Datasaurus Dozen. This one here. Kind of a similar idea. All the same, all the same linear regression line, same correlation coefficient, but wildly different shapes that you can make. So you do want to look at that scatter plot. It's an important step. It gets the name from this dinosaur creation that they made here. Okay, so that was the first step on that one. And I don't know why it does this sometimes. My iPad just restarted the apps. Let me pull this up again. All right, here we go. Okay, so that was just looking at the plot itself, this first step. An important step, for sure. Okay, now here's another example. And this is a couple of these steps I would expect you to be able to do on the test. And 4.1, 4.2 will have some problems where you do make predictions with your least squares line. So I wanted to review this in this section as well. A middle school band director collected data on students' practice habits and tested how fast students could play a piece of music. The data are shown below. Okay, decide whether it's appropriate to do a linear regression of this data. Well, thinking about the situation we're in, I would think it's probably not appropriate to use a linear regression, mainly because of how practicing and learning a piece of music at a certain speed may not be a linear relationship. What we can do is look at the data though and see what it gives us. So I'm going to copy and paste that in here. And get rid of the extra stuff. Okay, and it does look linear. Maybe kind of leveling off though over here. Residual plot, that looks all right. There's some up, some down. Correlation coefficient's 90%, just about. And those other ones look all right. So it is probably appropriate enough. Yeah. So I guess we'll say it's probably appropriate enough. Either way, we can make a prediction with this. So part B, let me just show you here. Part B here. It says if a student practiced 20 hours, student practiced 20 hours, predict how fast the student would play the piece of music. We're going to take this is the x value, x equals 20, we'll plug that in. And then one thing to note, look at all these ones. 6 is the highest, and we're doing an extreme extrapolation. So it's likely gonna give us a wildly inaccurate prediction. Also here, 200 beats per minute, this is y equal to 200 beats per minute. Also, extrapolation, not quite as bad, but it may give us a prediction for the x coordinate that's not accurate. Okay, so let me show you how to do that in this file. So I have the data in here over here, and I plug in 20. The prediction I would make is about 299 beats per minute, which is extremely fast. May even just be impossible to play it that fast. For that next part, the y is what's given, so our prediction for x, we plug in 200 for the y value, gives us 11.5, just about 11.5 hours.